call this science of measurement. Now, yesterday I made point to say something about system and surrounding. And the issue is the system is sending signals to you, the surroundings, as a detector. Now, the detector is calibrated and based upon data from the object of interest. This data is then translated into measurements. And what do measurements do? Well, they have a significant application, and you will recognize this in a very simple acronym, MALT, MALT. Any measurements give us meaning to the environment. And they answer questions. They limit behavior. And they are a functional tool for construction, building, and creativity. Building anything. You want to scale it up or scale it down or maintain a certain dimension or something. Well, you have to have some reference point to work with in that context. You know, we have to have certain conditions, especially in the scientific community. And so we'll call this one the conditions for measurements. And you'll see how this is used in the evolution of the systems of measurement in a moment. We'll get into that. So when we talk about measurements, a measurement is a signal from the system to you. And it has to make sense. And so in order to make sense out of the signal, three things are required. Fundamentally, it must define, or you must define, the fundamental dimension that is being described. Length, a weight, and a time. Those are fundamental dimensions. You haven't put any numbers in there yet, but you have to have something and understand what the difference is between a weight and a length, or a time and a weight, and so forth like that. You must select out of the fundamental standards from which everything else is compared. So in the metric system, we call it the SI system or the MKS system, meter, kilograms, and seconds. And one's length, well, everything's compared to meters. Kilograms, everything's weight related. And certainly seconds is time related. And in essence, once you have established this standards, then whatever measurements you make are comparative relationships. That is, we talk about a mile compared to 1 meter. And so it's not hard to think, oh, that's bigger than that, okay? Meters smaller than, less or shorter than the mile, and so forth. So this is the idea in any measurement, is to receive that signal and translate it into a numerical meaning and then translate that into, well, what is the object of interest doing? And so once you have a numerical explanation of what the object is doing, then you've made a measurement. And so that's the fundamental philosophy of how these things evolve fundamentally. Now, the content of measurements three things: a number, a unit, and an uncertainty factor. Now, we have two kinds of measurements that we're talking about in general. Our primary focus is the scientific measurements. And these require a number, a unit, and an error factor. So we have certain variations in the ability to make measurements, and that's usually inherent either in the observer or the detector, you receiving all the signals and what have you. And then absolute measurements. Absolute means exact. 5 apples in a basket. That's not much error in that. And so there are absolutes in the world of measurement. The ones, of course, we're interested in are up here in the scientific measurement. So what we want to do is focus on the concepts. Well, what about numbers? What's the deal with numbers? And what do we talk about when we talk about units? And what do we deal with in error factors? So one of the first issues that we want to take into account, and we know what numbers are, we can count, and certain devices we can get measurements. But in science, we wind up with calculations that may wind up with 2.347862591 on your calculator. There's a calculator in it. Well, how many of those digits really mean anything? Well, the digits that mean something are called significant figures, or abbreviated sig figs. These are all digits known with certainty plus one uncertain digit. So in the course of everything we're doing, it might turn out that we have it's accurate to that point where I made the mark. But we'll be using the half up. What I got, that means if it's 5 or higher, the previous number is scaled up. So this would then become 2.35 as a final answer, assuming we conform to the rules I'm about to talk about and some of the ways we deal with significant figures. Now, there are rules in significant figures, and you'll find these at the bottom of your outline here, and you'll see those. And those are kind of black and white and dry, as you expect. And it says here, all non-zero digits are significant figures. You can read them like I can't. All enclosed zeros, what all that means. You can read these all day long, memorize them, and you still miss out on a thing. But there is one way to deal with these that is far better than that I've ever seen. Memorizing a bunch of rules like this. It depends on where the zeros are and whether you have decimals or not. Say for numbers without decimals. You don't have a decimal place. and then number it all. Count digits left to right, excluding zeros. That's one rule. For numbers with, make it a little bit neater, with decimals, count the other way. Let's see, left. I think I got that backwards. I got that backwards. It should be right to left. I got my. Don't go get your money back. All right. So anyway, for example, if we have something without a decimal, like the distance from the Earth to the Sun, generally known as 93 million miles. But not all those digits are significant in the context. You got to have them all to specify everything. But what we refer to as the significant digits in there of dimension are just two digits. So we start right to left and excluding the zeros, 1, 2, 3, 4, 5, 6 zeros. And then when you hit the first non-zero digit, then you start counting. And any zeros that come in after that are significant. So this has two sig figs. That's all you got to know. And so if you have a 0.00123 nanometers, something like that, or meters, let's make it, don't get exotic here. You count from left to right. And you count until you get to the first non-zero digits. You exclude the zeros up to the first non-zero digit, and then list the number of digits after that. So what you would do is this one and this one are not significant, but this is 3 sig figs. And that's the long and short of it, this thing. Now, yeah, so everybody can see what's going on here. Here's some examples that we'll go through, and just for practice a second. How do we deal with this one? It's got a decimal in it. Which way we go? Left to right or right to left? Left to right, okay? So that's 1, 2, 3, 4, 5 significant figures. Everybody good? I'm not going to do them all. I'm just going to touch you. Okay, decimal. Okay, left to right again. That's 6 right there. Yeah, that's 4. And we can go fast as we want. Okay, is that a significant figure? The 0 right there. That's correct. That is not a significant figure, so that would be only 3 sig figs. Here's one with a decimal. Left to right would be 4. Left to right, this are not counted, but the last 3 are counted in that significant figure. Focus. There, sorry about that. Okay, that's a decimal, so left to right looks like 5 sig figs in that one. Left to right looks like 1 significant figure. Everybody good on that? Okay. Here, no decimal. Right to left, that's 1 significant figure because it's. Yeah, thank you. Right there. There we go. 1 significant figure there. Here is a decimal. left to right, so that would be 6 sig figs. That's a decimal. Left to right, that's 5 sig figs. And right to left, that looks like 6 sig figs. That one out there in the front, it says go till you hit a non-zero digit and start counting. And that. Okay, so just a quick review there. Any questions? Pretty straight. Okay, now we need to look at addition, subtraction, multiplication, and division. So your topic is sig figs and math operations. Okay, thank you, sir. And multiplication and division, round to the data point having the least number of sig figs. Okay, given 3.7 times 3.8. So this is the calculator answer, 90.06. But notice this is the measurement or data point in the calculation that has the least number of significant figs, sig figs, right there. So this would have to be rounded to 2 significant figures, okay? So what would that be? Well, since it's a decimal, right, left to right, so how many should we report the final answer as? So left to right, with a decimal would have to be 90. So there's only 2 significant figures with a decimal right here. Yeah, put the decimal in. Yeah, put the decimal in, back in. Or you really can't put another one in there, so it really just stops at 90. Because left to right is for your decimal containing numbers. I guess let's pick another one. Okay, this is a ratio of 1.678 divided by 0.42. So I get I promise what I came up with, okay? Calculator answer. Well, obviously that's not the way the answer should be reported. So when we look at this, both of them have decimals in them, so we'll count left to right. And so this has 4 sig figs, and the denominator has 2 sig figs. So this needs to be rounded to 2 sig figs, all right? Now, we use the half up, round up rule. So if I'm going to get 2 significant figures out of that, I would have to be right through here with this one rounding that one up and 4.0. And what's sometimes done is they put a bar over the number to indicate that it is a significant figure following that decimal position. So they're rounding to 2 sig figs in that case. Everybody see what it did? Okay. like I say, I can show you how this works easier than I can write out a verbal definition rule for this. So the problem is given to be 32.567, adding 135.0 and 1.456 and 7. So here is our calculator answer. Now, in this, we want to round it to the least number of digits to the right of the decimal. Well, what's that mean? The least number of digits to the right of the decimal would be this number right here, 135.0. So our rounding effect would be limited to that. We will round it to here. And so the final answer would be 169.0, with that being representing a significant figure in this type of problem. You see what I did? I looked at the least number of digits to the right of the decimal and round the final answer to that reference. And so that would reflect the positioning of your rounding, or how far to carry that measurement. As scientific notation. And so we discussed scientific notation. They are powers of 10. And when we talk about that, we're talking about expressing decimal fractions as well as that are less than 10, or decimal fractions that are greater than 10 or 1. So we're talking about and so or some number, which would be a number here times some power function. If n is greater than 0, then the number is greater than 1. If n is less than 0, the number is between 0 and 1. Long short. This doesn't count into negative numbers, but these are expressed as positive or negative exponents. So, and it's easier to show it than to write out long definitions and so forth. So if we have a number, a large number, 5,630,000, something like that, and there's no decimal listed in there, we assume the decimal is the end of the number, obviously, right here. Right there. Now, you can put that, move that decimal to the left, or even to the right, times a power of 10. If this is a number, as shown here, it's obviously a big number. And so we want to take that and move it back in this direction. Well, that would give you times 10 to a positive n value. Nobody said you couldn't move that number to the right, but if you move, however many times you move it, that's times 10 to a negative value. However many times to the right you move it. Now, and when you, in a practical context, we don't express numbers like that. That's with tongue-in-cheek, because if you're adding and subtracting, all of them have to be converted. All the measurements have to be converted to the same power of 10. And then you add the coefficients up, and at the same, and then you get the correct answer. You can't add powers of 10 if they're different. All right, we'll get to that. Okay. So let's say we move it to the position that's between the 5 and the 6. So that would be, assuming this position of the decimal is a 0 position, we count 1, 2, 3, 4, 5, 6 positions to the right to left. So this would become a 5.63, leave it at that, times 10, and we moved 6 places, and so we express that as a positive value of 6. Now, in this form, this is the coefficient, and this is the power of 10. When the coefficient is expressed between 1 and 9.999, whatever, between 1 and 9.9, is called a standard form. But that's just a common conversion that's used in the scientific community. However, I can move this decimal, say, from this position 1 place, or 2 places, or 3 places, 4 places. For example, if I moved it 1, 5,6,3,0,0 times 10 to the first power. Well, there's nothing wrong with that. That's the same number as this one over here, and the one that's given. Or move it 2 places, 5,6,3,0 times 10 squared. All of these are the same numbers. 5,6,3 times 10 the third. I may be getting ahead of myself here. 5,6,3. I move it 1 here. 1, 2, 3, 4, 5, 6. 5. That's right. 5 times 10 to the first. And then I would have, it's just a matter of counting them. Got it? Question? Well, here, I just cut off one of the zeros. I just moved it here. So that's 1, 2, 3, 4, 5, 6. I must have left out one. Yeah, that's where it is. Right there, another 0 there. And now it looks right. 0 times 10 to the third. I'm just illustrating. Now, typically you wouldn't be doing it. The primary form is like this. And 9 out of 10 problems, if you'll work, will be in that standard form. So you just move it to that position. And so, just to finish this out, 1, 2, 3, 5, 6, 3 times 10 to the fourth, 56 times 10 to the fifth, and then we're back to the 5.6 times 10 to the 6, which would be the standard form. So all of those are the same numbers. Depends on the circumstances you're using. Everybody agree on that out here? All right. Zero, 1, 0, 0, 1, 2, 3. Make it look neater. Like this. And in this case, the standard form, again, would be to place the decimal between the first and second digits of the number. And so in this, we would move this 0 point and 1, 2, 3 places to the right. Well, if you're working with fractions, it's a negative exponent. So this would give you, in standard form, to the -3, like that. Now, again, I could move it 1 place and maybe 0 point 1 place over 0, 1, 2, 3 times 10 to the -1, or 0.123 times 10 to the -2, or 1.23 times 10 to the -3. All these are the same number. It's just a matter of how you express the power of 10. But again, this would be the standard form that you would express the number in for the most part in a computation. Everybody okay on that idea? Okay. If you're multiplying exponential notation, you add the exponents, algebraically add this. If you're dividing exponential notation, you algebraically subtract the exponential notation. The way I illustrate this is I just pick a number, a big jumbled number, and just work in great detail through the computation. This will be the only time I'll ever do this in this class, but bear with me as we go through this. So let's take some number, answer, whatever it's going to be. So I'm going to do that, and 3.87 times 10 to the minus 4, 1.18 times 10 to the 7th, and 602 times 10 to the minus 11. Like that. Now, one way to deal with exponential problems that have a multiple of numbers like that is to separate the coefficients from the powers. What does that mean? You can set this up in the following way. Take your coefficients out, 2.51, and set them over here on the left. And then times ratio of exponents. If you've not seen this, this is a real neat little trick. Save you a lot of computation time. And you work with coefficients and get a number, and then you work with the exponents and get a number, and then you kind of move it to standard form or whatever form you want to put it in. That's the end of the problem. So, okay, so we get this digit, this number from the coefficient computation right here, and it's calculated, obviously. Now, when we work with these, work with them in terms of multiplication and division, I always work with a multiplication first, so we can set this up as a plus 3 plus a minus 4, then that was divided by 10 to the plus 7 plus a minus 11. So I'm adding exponents in the multiplication context right there. So then this then becomes 10 to the minus 1 and 10 to the 4, yeah. 4 like that. Everybody see that? Here we got 7, 8, 9, 10, 11, 4. The differential. We add back them. Minus 4, sorry. Minus 4. Now we have a ratio, so that would now be, wrong, 10, all right, minus 1 minus a minus 4 in that context like that. And so this would be times 10 to the, that becomes a plus, minus times a minus, add back 1, so that would be 3. And so we'd have all of this still hanging out over here. Let me put it to here. There we go. Okay, times 10 to whatever that times 10 to the third. Now, when we look at the computation, they're all 3 sig figs, so obviously we need 3 sig figs. And so 7 would cause the 6 to go up, and our final answer 1.37. would be your final answer. Now, there are plenty of opportunities in the worksheet to go through these. I obviously we don't have time in the lecture portion because I have too much other stuff to do, to cover and mention. But practice makes perfect, and so I would encourage you to find the worksheet on scientific notation, and it gives you many, many examples. I think there's 3 or 4 pages here that you can work through and develop your skill. Also, at the end of the heading text, in the appendix is a treatise on exponential notation, so brief. And so I would encourage you to do that if you need some more practice. And if you're still struggling, send me a note. We'll spend what time you need to master this. But it is a very important part of your learning curve that you master this now, because we're going to be able to use it just almost spontaneously in many of the future problems that we'll be working. So, systems units. When we define a system of units, it's defined in terms of fundamental quantities. Fundamental quantities are definitions that we're trying to measure. And length, weight, and time are the most common. But of course, we have other fundamental quantities, lumens, acoustic levels of sound, auditory audio. But anyway, I think there are about 7. But we are interested in these 3. So when we begin to define the systems of units, we start with these in fundamental quantities. And we'll build a table here. And we'll say length, weight, and time. And then we establish standards. We define, standardize, and compare. So when we standards, we divide into 2, English, systems of units, and metric, SI, Standard International, in that format. The Standard International used to be called the MKS, and for whatever reasons, it's consolidated into Standard International, so everybody had to use this commonly. But anyway, we all know what the foot is the standard for the English, weight is the pound, and time is the second, like that. Now, in the metric system, we find the meter, and then the kilogram, which happens to be a multiple, and is not the base unit, but we'll see that later, and kg. And again, time is in seconds. Like that. So it's established, and most of you already know this without question. The third element in the defining of a system of units is comparative. You compare everything with the standards. Now, one thing that we need to take a quick note of is these prefixes, are the prefixes, that are used with these systems. Okay, what you need to do to kind of see this in perspective we're going to make a vertical line like this. And right in the middle of it, this is where our standard's going to be. And we, from this point, is multiples of 10 or larger numbers. And below that standard are fractional numbers. As you go up and down. And we find that these are divided, say, into times 10, times 100, times 1,000, times 1,000,000. We don't have anything between that one. Times 10 to the 9th, and 10 to the 12th are the most common prefix designations. And we'll write them down here in a second. Now we go to 1/10, which is 0.1, or I'm running out of room here, or 10 to the -1. That one, move this over, and say we make 1/100th, which is 0.01, which is 10 to the -2, and then 1 over 1,000, 0.001, and that's equal to 10 to the -3, and then 1 over 10 to the 6, which is, of course, 10 to the -6. I'm not going to draw all that out. And 10 to the -9. We'll stop at that one. 10 to the 9th, and that equals 10 minus 9. Okay, what do these mean? These are blocks or fractions of the standard. So if standard's 1, then 10/1 is where we are, or higher, 100,000. Now, the designation is DEKA standard, decameters. That would refer to 10 meters. Okay, and you got hectometers. That would be a block of 100 meters. And then we have kilo, as we saw in the kilogram, that would be 1,000 grams. So we're still using it relative to a base unit. This is megameters, that'd be 1,000,000 meters. And then it'd be giga, or giga. You probably heard of that in reference to storage capacity of certain hard drives, gigabytes or terabytes, which is times 10 to the 12th. That's quite a bit. And those are numbers, again, larger numbers. When we get smaller fractions as we come down, it kind of parallels in some of the semantics of it. Deci. Oh, I use capital letters for the big ones. This is not a convention. It's just something I do. It's not required to be large capitals or lowercase. This is 1/100th is a centi. 100 cents in a dollar. Okay, and milli, micro, and nano. So this 1/100000th of an inch would be a nanoinch or something, or a nanometer, 1/100000th of a meter. And electromagnetic light waves are typically measured in nanometers. It's a very, very small quantities. But what are the three issues we just said? Okay, we've defined the fundamental quantities, length, weight, and time. Establish the standards, meter, kilograms, seconds, or foot, pounds, and seconds. And then did a comparison. Define, standardize, compare. So that's the essence of science. We always want to compare something with some standards. And so that's the essence of a system of units. have four primary topics I want to share with you. Standard conversions, percentage, and parts per million, parts per billion, what are they? Temperature conversion and energy conversion. So we'll be working with those 99% of the time. This I divide into three types of conversions. Simple conversions, multiple conversions, and complex conversions. When we talk about simple conversions, that's a single unit to single unit, unit to unit. Grams to pounds. All right. Seconds to years. So that's a single unit to a single unit. Multiples deals with squares and cubes. You're going from square inches to square centimeters. Okay? And then complex, these are combinations of fundamental quantities. You cannot convert pounds into seconds or meters into pounds. So it has to be retained in the context of the fundamental quantity. So these are combos. Now each of these has, say, a simple rules of conversion that you need to pay attention to. Now, that's why I've set them up like this. Now, you won't find them set up like this in your textbook, but it helps the students to understand and put things in perspective, because there's one little rule you apply for simple, and they have throw in another rule for the multiples, and then for the complex, there's another rule that makes the difference in your understanding of these things. So we'll start off with an example of simple conversions. And one that you have the greater experience with. And we'll say you're given 875 pounds, and the question is, how many grams does this represent? I use GMS like that. So I tell students to think in terms of the scientific method. What do you start with? The question, okay? And then you find information it's related to, okay? So this is question grams, and then equals where you're going. You're going to the grams, and then you are relating it to 875 pounds. Now, just a sidebar, and I'm sure you already know this, while I write it in this context, is actually 875 pounds over 1. Okay, so, and putting it in perspective so you'll understand exactly where it's going. Now, keep in mind you have a conversion sheet, and you just flip over. I will give you, and this is just some professors argue with me on this, but anything you can look up normally, I'm going to attach to that exam. Periodic table, you look up something. I see no. Where are you and where are you going? We need to get rid of, use one phrase, pounds. The only way to get rid of pounds in here is to divide it by pounds. So pounds divided by pounds. And so I put a times sign, line, or block bracket, depending on what you've been taught in the past. I don't care how you do it. It means the same thing. So if you set it up with pounds here, and then on top, decide on where you're going. Well, if you have a direct relationship between pounds and grams, great. Maybe you don't, and we'll work another one in a minute. You don't have, you have to make multiple steps to it. There is a relationship between pounds and grams where you're going, and it turns out to be 454 grams equals 1 pound. And when setting this up, be sure to get the right number with the right unit. You don't want to set it up in some context like this. Does that make any sense to you? You see what I'm telling you? Just don't make that mistake. From a practical standpoint, 1 gram is an itty bitty, and 454 pounds of cow size, you know. So you got to, that would be backwards. But 454 itty bitties equal 1 great big. Now, the pounds drop out, and you're left with the units that you need to find. And so, I'm going to get rid of this right now. It'd be 875. Oops. 875 times 454, and we'll put grams. And so that looks like 397250. Grams. Now, we need to express this in the proper number of significant figures. Well, both of them are 3 sig figs, so this would be 3, we round it to that point, so this would be 397,000 grams. Reading right to left, that would be 3 sig figs. And if you wish to put it in exponential notations, 3.97 times 10 to the 1, 2, 3, 4, 5, positive 5 grams. So however you want to express the number. One way to do it. One problem that uses multiple conversion factors is converting your age to the years into seconds. How old are you in seconds? So we'll take an average on that. Okay, say you're given age to equal 20 years old. How many seconds does that represent? Kind of an interesting thing. How many seconds do you think? So, how many seconds equal 20 years? And so we want to get rid of years, so we'll start with a time sign, a line, or a bracket, however you want to do that. And be sure years is on the bottom. Anybody know second-years relationship? I don't. So, but I do know there are we'll use 365 days in a year, so we get rid of that dimension. And we keep going until we reach the objective. So that would be days, and I'm going to use hours. Now watch how I do this. I know I'm going to get rid of days, go to hours, but that's not where we want to be. We go hours, and I do know there are minutes. I'll go use that one. And minutes goes to seconds. So I can just kind of lay out the dimensional ratios until I get to the desired dimension, then go back, put in the numbers. Know there are 24 hours in one day. There's 60 minutes in an hour and 60 seconds in 1 minute. And then go through and cancel the units until we reach the desired number. And of course, our age in seconds is, everything's in numerators in this one, isn't it? 20. Doesn't always turn out like that. 365, 24, 60, 60. It comes out. And seconds. I'm glad everybody understood. Yeah, y'all keep me alive here. Okay, that's an example of course, the simple conversions, a couple of examples. And I would encourage you to get into the worksheets and make sure that you can deal, and they have many variations in there and so forth. The second type of conversion will be the squares and cubes. when working with multiple conversions, there's one little trick that makes all of this come together very quickly for students I've found in the past. Solve the problem as though it were a simple conversion, and then square the conversion factors, because the data point's already squared. Think about it. All right, or cubed, however I'm thinking. Okay, let's say you're given 35 square inches, and what you want to know is that in square centimeters, like that. Let's make it feet. I'm sorry, let's make it feet so we can throw in a couple of conversion factors. 35 square feet, and you need it in square centimeters, like that. So we set it up as a simple conversion, like you're converting from centimeters, from feet to centimeters or whatever. And so I start out with how many centimeters is going to be squared, but is equal to 35 feet squared. I'll go ahead and put them in there. I'll show you what I'm going to get to. Now, ignore the power up here for the moment and go through the simple conversion. We want to get rid of feet, and we go to inches, and then inches into centimeters. And then put in your numbers. 12 inches in a foot, and it's 2.54 centimeters in 1 inch. So jot that down if you make a note of it. I'll give you a second. Is square the conversion factor. See, the data is already squared. You don't need to do anything to that. Put brackets or parentheses, and that'll solve the problem for you. Right there. Just square each one. And so it scales it to the square, and then you cancel out there. So to spread this out a little bit, it'd be 35 foot squared. It'd be 1 squared foot squared, just to emphasize. And then this would be 12 squared inches squared. And then this would be 2.54 squared. Put parentheses if you would like. And be 1 squared over inches squared, like that. So that's what it evolves. And so that cancels nicely, that cancels nicely, and that leaves us with the dimension we need. And so it would be 35 times 12 squared times 254 squared, and come out centimeters squared. Punch it in the calculator, and answer is relative to, looks like 2 sig figs in this. I keep getting turning back, I'm sorry. Now, third type is complex conversions, in which you're dealing with combinations of fundamental quantities. One is density. We will use that in our lab thing. Density of substance is a characteristic of a pure substance and is defined as a mass per unit volume. And if you're working with, say, cubic centimeters and a mass in grams, you can't convert one into the other, so you have to leave them in the appropriate units given. So let's say we're given 238 pounds per cubic feet. What is that in grams per cubic centimeter? The rule here is to make a simple conversion, or in the case multiple conversions, convert one dimension at a time. When you finish that one, then you go back and convert the other one. And then you combine everything into one computation with the appropriate units. For example, what are we looking for? We're looking for grams per cubic centimeter. and we have, I'm going to put this 238 pounds per cubic feet. And so we're going to grams first. And so I'll put pounds down here, grams here, and it's 454 grams per pound. And pounds cancels out, and so we're at the appropriate unit as far as one of the dimensional fundamental quantities is included. And then we go to, we've got, we'll fit up here, and we'll do a simple conversion, and then cubic conversion factors. Okay, and we got inches, and centimeters, and that's 2.54, 1 inch, 12 inches, and 1 foot. Then we'll cube that one, cube that one. That one doesn't need any cubes, and so cubic feet, let's see, inches will drop out, cubic feet will drop out, and so we're left with cubic inches and grams per cubic inch when everything is checking. But convert one at a time. And so extracting the numbers, that'd be 238 times 454, and then we have 1 cube divided by 12 cubed, 2.54 cubed, and everything's going to come out in grams per cubic centimeter. That's shown here. That's what I got. Okay. And so this times this divided by those two. I might come down here with it. There is our calculator answer, and if we look back up here, we only have 3 sig figs, so we would round it to 3.87. As our appropriate answer. Here we have percent, parts per million, and parts per billion as conversion factors. Actually, all of these are essentially the same thing as far as the mathematical relationship and everything. Percentage, by fundamental definition, is part over total times 100%. And actually, this is parts per hundredweight. Okay? And most of you already recognize that. That's something you grew up with. But parts per million, parts per billion are not quite as familiar. But when you look at it, parts per million is the same thing. However many parts you're talking about, you have a mix of red balls, blue balls, and green balls. You take the red ones over all the, over the total. But this time, instead of times 100, it's times 10 to the 6. and that gives you parts per million. Parts per billion is simply the parts involved over the total parts times 10 to the 9th. And so that's the essence or fundamental definition of each one that we're doing. The need here is converting from percent to parts per million or parts per billion, or vice versa, going from parts per million back to percentages, whatever you need. So it's a conversion issue as we are using it. Kind of problem you would have, say you're given 0.00387% by weight, and you'll see a symbology like that. It means it's a weight-weight ratio. There's volume-volume ratios and mass-volume ratios and so forth. And most of what we use is weight-weight ratio, and it's designated W/W, or weight percent. People put those on there also. Now, the idea is, how do you convert that to parts per million? Parts per billion. Well, to do that, you need to understand what percent means. When your problem says given 0.0037%, what does brain say? Brain should say 0.00387 divided by 100, because that's exactly what it's telling you. So this is actually 0.00387 parts per 100 times 100 would give you what? The percentage. But we need it in parts per billion, and by this parts per million. For this definition, we simply multiply times 10 to the 6th, and that'll give you the parts per million. Or if you want it parts per billion, you do the same thing. What does it mean? 0.00387 over 100 is what it means. Multiply it times 10 to the 9th is the issue. And then you've got your conversion done. From that standpoint, that's actually 10 squared. So you bring it up minus 2, subtract 2 from that, and it's 0.00387 times 10 to the 4th. And we can convert that again by moving to the right 3 places. So that would give us 3.87 times 10. We subtract 3, 10 to the 1st. Yep. And so that's 38.7 parts per million. And we didn't do anything that we haven't done already. Just moving the decimal to the right or the left. If it's a fraction and you move to the right, you subtract your exponent. Move to the left, you add your exponent. And in this case, we had to move to the right and to consolidate the number. And I'll leave this one to you. Here's just 10 to the 9th, and so it's a couple, 3 more, maybe 3870. No, 38,700. If you are going the other way, trying to get parts per million into percentage, or parts per billion, recognize parts per million for exactly what it is. So many over 10 to the 6th, or so many over 10 to the 9th, times what for percentage? Times 100. So let's say you're given 21.75 ppm. What is this in percentage? Well, recognize the data point for what it is. It's telling you that X is equal to 21.75 over 10 to the 6th, whatever they are. Now, the units will cancel out of that. And the only thing you have to worry about is multiplying times 100 and putting a percent symbol on there. That is if you're given parts per million. If you're given parts per billion, what would that be? 10 to the 9th. And then times whatever you're going to. Now, if you're going from you could do the same thing with converting from parts per million to parts per billion, right? So you'd have 2.75 over 10 to the 6 times 10 to the 9th. And so that's how simple this system is. But you must understand what percent means, or what parts per million means in the big picture, and making the conversion. It means just what it's telling you. And once you get used to it, you'll see that 15.7. Let's say you're given salt solution that's 15.7 weight percent salt. What is this in parts per million and parts per billion? That's kind of obvious. It's very basic. So by recognizing what 15.7% means, all you got to do is multiply times 10 to the 6, you're through. Or 10 to the 9th, you're through. That make sense? Okay. Don't make it more complicated than that. That's the objective of this. To convert from parts per million, parts per billion, percentages back and forth. Okay. Temperature conversions. Now, it's kind of a foregone conclusion. Before you even walked through the door, you knew you were going to have to do dimensional analysis and so forth and so on. But you will have lots of temperature conversions as well as energy conversions, and that's the last two topics today, and completes our work in chapter 1. In temperature conversions, you are dealing with degrees Fahrenheit going to degrees Celsius and going to Kelvin. Kelvin does not have a zero on the little circle superscript. It's an absolute. And then back and forth. So you need to understand the formulas. Now, most people have a conversion on their calculator, and they don't worry about it that much. But it's my obligation to present the equations. If you're going from degrees Fahrenheit to degrees Celsius, you want to use degrees Celsius is 5 over 9 parentheses degrees Fahrenheit minus 32. That's the old classic formula for that. And if you're going from degrees C back to degrees Fahrenheit, you want to go degrees Fahrenheit is 9 over 5 degrees C plus 32. You don't have a parenthesis in that one. So I look at it to memorize that. The C looks like a parenthesis, right? So it's the one with the parentheses in it. F doesn't look like a parenthesis, so it doesn't have one. Like that. Also, if you're the numbers, if you're going degrees Fahrenheit to Celsius, you're going downhill. So 5/9 is a smaller number than the 9/5. It's just a memory device. And if you're going from Celsius to Fahrenheit, you're going uphill, or a bigger number, 9/5. So it's just something I remember the formula of. Now, the only other one is your absolute Kelvin temperature, which is degrees C plus 273. But be sure you can get degrees C to equal Kelvin minus 273 if the problem asks you to go from Kelvin to Celsius. Okay, where do these come from? Okay. Now in this, you want to draw a two-dimensional graph. So we'll put Fahrenheit on the vertical, and we'll put Celsius on the horizontal. And then we mark off the points where we would find the boiling point and freezing point. Well, if this is 0 degrees Celsius, and we'll say we'll come up here to, I don't know, right there, 100 degrees Celsius, and we'll start here, say that's 32 degrees Fahrenheit, and 212 Fahrenheit, right there. That's the boiling point, the freezing point. Well, we'll make X, this, where's my point? So this is 0 and 32, right there, right there. And this one is 100 and 212, right there. And so we draw a line through those two. Like that. Now, using the point slope, which is x minus x prime equals a change in y over change in x, and y minus y prime, where the prime values are defined, and x and y that are not primed here and here are not defined. And we solve for the appropriate x or y. Okay, so if we're using the horizontal, which is Celsius, then this would be degrees C minus, all right, we'll take 1 point here, 0, x1. We'll use the first. And that one is equal to change in y, which is 212 minus 32, divided by 100 minus 0, which is your slope, right here, and then degrees Fahrenheit minus the 32, like that. So that sets it up. So solve for C. That gives you your C to, based on F. And then turn around, solve for Fahrenheit in terms of C. And that gives you Fahrenheit conversion. So let's see what we got. So degrees C now is equal to, that's 180 over 100 degrees F minus 32, and that's 9.5. Is that what I did? Yeah. Well, I want to make that 5.9. Added that to it. Sorry about that. It happens. So that would be degrees Fahrenheit minus the y prime, which we're going to use that 32 now, is equal to 212 minus 32 over 100 minus 0 now. Sorry about that. I hate to make mistakes like that. Degrees Celsius minus 0. Now we got it. And we solve for Fahrenheit in terms of Celsius, degrees Fahrenheit. And so that would add 32 to both sides, 0 drops out, and that would be 180 over 100 degrees C plus 32, and that would become 9/5. I saw that when I finished the, now that's the top one. Or solve for C, degrees C, divide both sides by that ratio of 9/5, and it inverts to 5/9, but you have to keep the parentheses around the Fahrenheit minus 32, and so that's where they come from. Subtract, notwithstanding my stupidity, it's y minus those two. Anyway, that's where those two equations come from. And I don't need to work problems on that. You know how to plug and chug through these types of problems. byproduct of energy. Temperature is not energy. It just says that an energy change has occurred. Energy, by definition, our physics friends, is simply defined as a force times a distance. Is what our physics friends call it. And they also tell us that Newton's second law says that force, F, is mass, m, times acceleration. ma, at force equals ma. Now, if we substitute this mass times acceleration into this expression, we get energy to equal mass times acceleration times a distance, like that. Well, acceleration, A, is a change in velocity, or change in velocity over a change in time, and velocity is a change in distance over change in time, or change in distance over change in time squared. Now, you're not going to have to work the problem out. But what I'm trying to show you is that when we put change in distance over time squared, we'll just make it distance over time squared. What we have here is E equals mass times distance over t squared times another distance, which gives us a mass distance squared over time squared. Okay, in the SI system, energy now is kilogram meter squared distance over second squared. That's what energy is. And that's too complicated for us simple scientists to use, so everybody says, okay, we're going to call it a joule. That's where I'm going. So that's how you get from the definition of energy into the units, what we call the joules. 1 kilogram meter squared per second squared. Please pay attention to that one, because we'll use that a few times in the future. Matter of fact, I usually give one of those as a conversion problem on the exams. Convert from so many kilograms to something else, and whatever. The other unit, and we'll show you the relationships that you need here in a second, is the calorie. The calorie, there are two kinds. There's a nutritional calorie, and then there's a scientific calorie. We're talking about the scientific calorie. Nutritional calorie is 1,000 calories, scientific calorie. The scientific calorie is the amount of heat, energy, needed to raise temperature of 1 gram pure water by 1 degree Celsius. That's what a scientific calorie is. Okay, who cares? Big deal. What do you need in terms of conversion? The relationship is between calories and joules. This is where it kind of comes together. 4.184 joules equals 1 calorie. If you look at your conversion sheet that I gave you earlier today, at the outset of class, you'll find that little conversion factor on there. And so many times you'll be making conversions to joules, kilojoules from one or the other. So it's a dimensional analysis, but I wanted to always try to at least show the classes where these numbers come from, or these dimensions come from. Now, you're not going to have to come up with kilogram meter squared over second squared and use that in the problem. But you now know where it comes from and can recognize it. I put stuff like that on those quizzes. which of the following is a complex unit for joule? Kilogram meter squared over second squared. That kind of stuff like that. That's fine.